So I will be presenting a couple things. I'll be presenting JWST in MAST. So this is what the MAST interface would look like. I've already searched for my file and found what I'm looking for. So that's this one right here. And on the left, you can see a few different buttons that give you different options. You can download the file, add it to a basket. And then the icon right here is the option to visualize the data product in one of the JDAVIZ configurations. So this X1D file can be loaded in Specviz. So if I click this icon right here, it will open up a MAST interface. You can see the Specviz instance on the right side, and then information about the data on the left. So Ricky did a good job covering the UI. There is the app-wide toolbar up here at the top, and then the viewer-specific toolbar here in lighter blue. Data drop-down, and the same zoom options. So not a whole lot more that I can talk about here, but this is what that interface would look like. So if you would like to interact with the data, you can download this notebook. So that option is up here at the top right, open data in Jupyter, and then that would download the Jupyter notebook. Here at the top, this is the information about the data. And below this section right here, it shows you what your notebook will look like if you download it from MAST. The difference being that this will look like code. Right now it's raw, but it would look like this. And you would have these 4 cells. Running this one would prompt you for a MAST token, which you can click a link, enter the token, and then you would be able to see your data in Specviz in the notebook. And I'll be talking about why that is helpful. So let me move on to the actual Specviz demo. We'll start by running the import calls, getting our data, and then loading it into Specviz. And right here, there's a few helpful things you can put in here. One of our attendees yesterday actually printed out, like, there's a bunch of different options. If you don't want it on the right side, you can just remove this completely and just have the Specviz instance right below this cell and keep it in one place. But for the purposes of this demo, it's easier for me to have it on the right. So another thing from our attendees yesterday is we had quite a few people that were coming from non-astronomy backgrounds. And I think that's awesome because I also have a little bit of an astronomy background, but mostly a development one. And my colleagues told me that this is a very interesting spectrum because you can see a clear triplet of Gaussians here, which is an emission line that is, or 3 emission lines that are unique to galaxies. And what's interesting is that they appear to be very highly redshifted. So during the course of this notebook, we'll be trying to get a sense of just how redshifted this galaxy is. So to start, we'll actually highlight this emission line right here, and that is the H alpha. So what I'll do here is I'll use an API call that we have available to create a subset on that emission line. And then because this subset is linked to the data, we can have them interact and use them in plugins together. So of the 3 things I just said, some of that might not make any sense. So let me backtrack a little bit. And what is an API? An API is something that allows a user to use code to interact with an application and retrieve information and data, and then use that with other programming tools. A subset in the case of JDAVIZ is a geometrical region of interest. So here we just have this X range of points that are of interest to us within this subset. And you can change this subset at the top, and I'll show in a little bit another way that you can make subsets and make them non-continuous as well. And then linking is a tricky subject, and we'll be talking about that throughout these presentations, but essentially it tells JDAVIZ how 2 data are connected. So if you have 2 spectra and you link them along the spectral axis, they will both be visualized in Specviz, and assuming that they're the same units, you can visualize them both at the same time, have them interact, use subsets with them. So each configuration in JDAVIZ, whether it's Cubeviz, Specviz, Imviz, Mosviz, has a helper class. And that helper class gives access to certain convenience methods. For example, you can set the x limits using specviz.x limits, or set the y limits using specviz.y limits. And I can show that right now here. And this may help the person with problems zooming out, because you can set the x limits to be much higher, and then it'll zoom out. Another very helpful API is the .plugins. So specviz.plugins, which I'll talk about here, gives you access to all of the plugins that are loaded in a Specviz instance. So all the plugins here have at least some user API calls that can be made on them. And in order to access those plugins, you would just do specviz.plugins and then the name of the plugin. If you ever forget what helper methods are available, you can do a dir specviz, and then that tells you all of them here. Okay, so we'll move on to using the first plugin. So this will be the line analysis plugin, and that will give us some specutils analysis for a single spectral line. So we'll pick the H alpha line that we created earlier, and the continuum is off here. And the way we can make one that makes sense is to create a new subset and use that for the continuum. So I've clicked on this select range of x values button, and you can see at the top it's no selection. So that means it's going to create a new subset when I click and drag. So I'll do that here. Okay, and I've made one half of the continuum on the left side, but I want to make this on the right side as well. What you can do is go to this button right here where it says select, create, delete, and you have options here for how you want your subsets to be applied. So we'll click on add, and now we'll be able to click and drag and have the subset cover the two opposite sides of these emission lines. And now we can use that for our continuum. And that makes sense. And here you can see some of the specutils analysis that we were talking about before. And so let me set this plugin variable. You can also, as I said, use the API here to see what options you can have, and then set some of these values programmatically instead, and then also get the results back programmatically. Okay. So yeah, we'll move on to the model fitting plugin. So what we'd want to do here is we want to create a model that shows these three emission lines in the context of the spectrum. So to do that, we actually want to make a new subset here that can cover the continuum and the triplet of Gaussians that we were talking about. So we'll make this new subset 3. And we'll base our models on that subset. And we'll start with a linear model. And then we'll add 3 Gaussians to cover the 3 emission lines here. And then you can actually go in. These are estimates for the values. And if you want to, you can go in and actually set them to be exact. So we want to get the exact values of the peaks. At the top here, you can see the value of the cursor. At that point, you can see the wave and the flux. So we can use this to measure each of the peaks and then set those values here on the right. I'm going to skip that just for the sake of time. And you can also do all of those things programmatically as well. So these 3 cells here do what I did in the UI, which is just create the linear model, create the Gaussian model, and then the 3 Gaussian models. And then this here just sets these values over here. So we'll set that, and you can see that updated here, the new mean, the new standard deviation. Do the same for the second Gaussian and for the third. You can see these values mirror what is over here. And then we can click Fit Model at the bottom of the UI and see what the model would look like. And also turn off the data and just see the model if that is helpful. That looks pretty good. And as I said before, you can do the same thing with the UI here and get the information plotted out here as well. And this is telling you the fitted model here, and then this is the fitted spectrum here. And all that is in our documentation as well. I'll move on to the line list plugin. So this tells us, well, this allows user to plot wavelengths from a preset or to create custom lines. So we'll plot from the preset galactic 2000 angstrom to 11,000 angstrom, since this is where our spectrum falls inside of. And then we'll load this list. There's quite a few lines in this one. So what I'll do here is in our UI, there is a search option. So I'll search for the H alpha line. And then also the N2 lines that are on the left and the right side of that. So there's a few different ways we can get an estimate for this redshift. We can look at where this appears to be. So this is in micron, but if we were to convert it to angstrom, this would probably be about 22,600, let's say. So we can type that in here, press enter, and you can see that these three lines are now pretty close. So that was a pretty good approximation. If we scroll up to the top of the line list plugin, we can now see this redshift slider, and we can use that to try and get a more accurate sense of just where it is. And I think that's pretty close. But there's actually another way that we can use some of the tools we've already demoed to get the most accurate redshift. Maybe not the most accurate, but very accurate. And to do that, we would go back to the line analysis plugin. That's the first plugin we looked at. And at the very bottom, there's an option to redshift from centroid. So if we select the H alpha line and then assign that, you can see that it lines up pretty well. Let's see if I can a little clearer. And that is our estimated redshift for this galaxy. And that is all for Specviz. Thank you all.